My name is Joe Conway. This talk is Fun with Functions. I work for a company called Crunchy Data. We do Postgres services and support. Just a side note before I get started. The number of slides I have for this talk are actually far too many for an hour, for 55 minutes or whatever it is I have. So what I've done in the past is I've taken a lot of the examples that are kind of at the end and moved them after the questions. And the point I want to make is that on the Postgres wiki, there's a page, if you search for like Postgres wiki conference presentations or something, you'll come up with this page. I just talked to the conference organizers. This link wasn't there until a few minutes ago. I just added it. But this is kind of where the Postgres community tends to put slides from talks, and my slides are already up there. And so for the part of the talk that I'm not going to get to today, you can download my slides. All of the examples you can cut and paste. And hopefully the rest of the conference will follow through and add their slides to the same place too. So first of all, how many people in here have used functions in Postgres before? So most people have. That's good. They're full-fledged objects in Postgres, and the thing to realize is that a lot of the underlying functionality in Postgres is actually implemented on top of functions, and that it's a fundamental part of the Postgres architecture. So the ability to write functions can be quite useful in ways to extend Postgres itself. They're created obviously with the create function syntax, but they can be used really in all three major parts of a query. They can be used in the target list, they can be used in the from clause, and they can be used in the where clause. And we'll see examples as we go through of all of those different types of uses. What are they used for? Obviously functions are used in and of themselves as functions, but basically all of the operators in the system, if you take 2 + 2 = 4, that plus sign is really just a representation of a function. There's a function underneath the plus sign. The data types, all the data types have functions that are used for taking the data in and storing it, as well as expressing the data back to the user. So when you store a timestamp, it's not actually stored as a string that looks like the timestamp. It's stored as a binary value, and then when you pull it back out of the system, it gets turned back into this readable string. And the functions are what are doing that. All of the index methods, casts going from one data type to another, triggers, aggregates, ordered set aggregates, and window functions. These are all examples of things that functions can be used for in Postgres. They can take a lot of different forms, and we're going to kind of the point of this talk is to go through all the different forms that functions can take, so you have an idea of the breadth of what you can do with them. But basically, if you break it down, there's kind of 4 basic type of functions. There's pure SQL functions. There's functions that are written in procedural languages. There's internal functions, which are basically the ones that are just built into the Postgres backend when it gets compiled. And then there's C language functions, which are extensions that can be loaded in but have been written in C. I should note also, another thing I've done on these slides is I've tried to include links into the documentation for the relevant sections on a lot of these slides. So again, if you download the slides, those links are live. Arguments to functions can be base type, composite type, or combinations. Now, who here is not familiar with that terminology? If I talk about a composite type, does everyone know what that means? Anyone not know what that means? Okay, so basically you can pass an entire row reference into a function as an argument. You can pass individual base data types like int or text, combinations of the two. The arguments themselves can be scalar, which means a single element, or they can be arrays of elements. There's also this idea of pseudo or polymorphic types. We'll get into those later on in some other slides, but basically what those are, not real data types, but representations of data types. Variadic, which means you can define basically an argument that can be any number of elements as long as they're all the same data type. And then they can be marked as being in arguments or out arguments or in out arguments. And again, we're going to see a bunch of examples of all this if you're not familiar with it as we move on through the slides. The returns can be a singleton. So in other words, it's just a single value returned from the function, or it can be a set. They can be base or composite type, and they can also be pseudotypes or polymorphic types. Any questions about that before I move on? So SQL functions, basically you could have a list, an arbitrary list of SQL statements separated by semicolons, and whatever the last statement is in the SQL function is what's going to determine what gets returned by the function. They're very similar to other functions in that they have a way to pass argument names in and be referenced inside. So you can reference the first argument is $1. You can also name the arguments these days. Back in the early days of Postgres, when I first started using it, you couldn't do that. You had to basically say $1, $2, $3. Now you can also name those things. If you pass in a composite type, you would reference it as $1 dot column name, essentially, or argument name dot column name. But in SQL functions, you can only use those arguments as data values, not as identifiers. So in other words, you couldn't pass the name of a table into a SQL function and then select from that table. You could do that with something like PL/PG SQL. Fortunately, we're not going to have time to get into those kinds of examples in this class. I think Jim Legensky gave a talk on PL/PG SQL. Hopefully you saw that, and he probably went into that kind of detail. If the return type is just a singleton, then you'll get just the first row of the last query. And if there is no result from that last query, you'll just get a null back. But if the function has been defined to return set of, which means potentially multiple rows, then it acts more like a set operator. You'll get all the rows from the last query, or you'll get an empty set if there are no rows. So there's kind of a subtle difference in behavior. Whereas if you've got a singleton return type, you're going to get a null if nothing's returned. But if you have a set of, you're going to get no record at all. Procedural languages are, again, these are user-defined functions, but they're written something besides SQL or C. The task is passed to a special handler. And again, that handler actually turns out to be another function. So you pass the task into this other handler, and this handler will get dynamically loaded. And it could be something that's like PL/PG SQL is just self-contained. It's got its own parser. It's distributed with Postgres, and when you run a PL/PG SQL function, that binary gets loaded and things get executed by that binary directly. But if you're using something like PL/Perl, then the handler function is actually linking to something external on your system, like Perl or Python or any number of other things that people have written procedural language handlers for. Internal functions are statically linked C functions. So these are the functions that are built into the Postgres backend. There's really not a whole lot that you're probably going to do with these, but I do mention it because you could potentially reference one of those internal functions in your own create function, marking it as internal, and basically in effect you could rename it. So DSQRT is the double precision square root function in Postgres that's built in. If you wanted to rename that square root, you could do it just like this. C language functions are user-defined functions written in C. They're compiled into shared object libraries of some sort. Depending on your platform, they might be a .so or a dylib or a DLL on Windows. These things are loaded into server on demand. They'll only be loaded once. The first time you call any function that's in a given library, it'll get loaded, and then it'll never get loaded again, so you don't have to worry about that. If you want to write these things, look in the contrib folder in the source directory, in the source Postgres source code. And not all of those, but quite a few of those are essentially C language extension functions. And so those are a really good source of examples if you want to write your own C functions. It's a fairly complex topic. You need to put this PG module magic call in there. Use the same kind of call conventions as the internal Postgres code to the extent that you can. But really this topic could be a whole full day tutorial all by itself. So I'm not going to try and get into a whole lot of the detail of it. Yes?
Is there any way to load a C language like shared object that was built for a different version of Postgres? Or is that
No, this PG module magic is designed specifically to prevent that. And that's because years ago, actually, there was no PG module magic, and periodically people would upgrade their Postgres installation to a newer major upgrade, major version, and they would try and use C functions that had been compiled on the older version with the new one, and sometimes that worked okay, and sometimes it didn't work okay, and they were often very difficult to debug strange behaviors that would happen. And so generally speaking, if you're running something that's compiled from C, it needs to be compiled against the same version of Postgres that you're running, and that's what this call enforces, basically. So today, if you try and build a C function and load it without that, Postgres will complain. Any more questions? So Postgres itself ships with these four server-side procedural languages: PL PG-SQL, PL Perl, PL Python, and PL Tcl. And PL Perl actually comes in two different flavors. It's got a untrusted Perl and a trusted Perl. I don't think I actually have a slide on this, so why don't I just talk about it for a second here. The difference between a trusted procedural language and an untrusted procedural language may sound a little counterintuitive, but if you have an untrusted procedural language, you should not give access to create functions in that language to anyone who is not trusted. So in other words, if it's an untrusted language, super users can create functions, but normal users shouldn't. And that's because an untrusted procedural language can reach out and do things on the operating system. Basically anything that the Postgres operating system user could do, which includes deleting database files or whatever, could be done potentially by that function. If you run PL Perl untrusted, you could delete files. You can do anything that the Postgres user, the user that Postgres is running under, could do on the system. Whereas a trusted language specifically has been vetted to not allow that kind of thing to happen. So PL PG-SQL, you can give access to untrusted users to write PL PG-SQL functions because they can't get out to the operating system and do anything bad. Does that make sense? There's a bunch of other procedural languages available. There's a PL Java, PL V8, which is basically based on Google's JavaScript, PLR, which is something that I wrote and have been maintaining for 13 or 14 years. And there's a bunch of others. I think there's a PL Ruby. Peter Eisentraut, who's walking around somewhere, wrote a PL Shell. So you could literally, talk about untrusted language. You can run anything at the shell right from a function. Hey, Jim. Yeah. Well, generally speaking, if you can write it and compile it in C, it's probably going to be the fastest. Of course, that's highly dependent on how you write your C. So there's lots of tricks you can use, sort of if you're familiar with the Postgres backend code, to make sure things are done efficiently and cached. And so if you study some examples that do that sort of thing, you can make your C functions really, really fast. Of course, you could also write your C functions poorly, in which case, the PL/PG-SQL might actually beat it, because PL/PG-SQL is actually pretty quick, and the first time you execute a function in PL/PG-SQL in a given session, it actually gets cached. The compiled kind of the pseudocode or whatever is cached, and so future runs of that same function within the same session tend to be a fair bit faster and pretty darn close to C speeds. Jim, you've actually studied this, right? So.
Yeah, it's starting up the first time. It is a noticeable difference in PL/PG-SQL versus C. But after you run it a couple times, it's cached, and all the SQL statements become planned. There's not that big of a difference. As long as you're not doing complex operations inside of PL/PG-SQL, if you're doing select statements and doing little things, it's not that different.
Yeah. And the other thing that you can actually do, and again, I don't think I have a slide that mentions this, but there's in PostgreSQL.conf, there's something called shared preload libraries, or preload shared libraries. Or first one. I should know, because I actually wrote the patch for that, but the basic idea is you can take one of these shared object libraries and cause it to get loaded when Postgres first starts up. And if you know anything about the architecture of Postgres, when a client connects, the postmaster just forks. So anything that's running inside of the postmaster is already there for free, essentially. So if the load time for that first time the PL/PG-SQL.so gets loaded has a noticeable impact in your environment, you can actually preload that thing, so you'll cut down even more on what that first execution will cost you. So this is the syntax for create function. Obviously, it's fairly complex. Provided I don't move too slowly, we're actually going to touch on pretty much every one of these things. I know there's a lot to look at here. I'm not going to try and go through it here on the screen. We're going to go through it one item at a time. But before we do that, I just want to do a little side note. Who here is not familiar with dollar quoting? Anyone? It's great. Everyone is at this point. I've been in some talks before where like 3/4 of the people had never heard of dollar quoting. So I won't, suffice it to say that for creation of functions, dollar quoting is very, very useful. Another sidebar is anonymous functions. A few releases ago, and I'm not even sure when it came in, it might be that all of the supported versions of Postgres now have this. Came in probably around 9.1, 9.2. You can actually sort of define a function on the fly without a name and have it execute. It's kind of limited in what it can do because you can't pass it arguments and it can't return a value. But for kind of administrative things, and I've got an example here, this do loop basically is going to run a query against the roles, figure out which roles exist that are part of a group called admin, and then for those roles, it's going to bump up the work mem for that role. So anytime a role that logs in that's part of the admin group, they automatically get a higher work mem. And that would be a bit tedious to do if you had a bunch of people that were in that kind of role and you had to do each statement. But this is kind of a convenient way to do some admin stuff that you can put into your scripts.
This setting of the work memory, is that just for this session only?
Well, if you set work mem through an alter role statement, it actually binds that setting to that user. So whenever that user logs in, they automatically get that setting. And you can do that basically with any of the settings that are session settable. You can alter a role and assign that to that session. You can also do the same thing with a database, and we'll see later you can do that with functions. You can assign values to functions. So in that example here, again, here's the query. If you're interested in studying this later, this basically shows all of the users that are in the group admin along with any custom settings that are assigned. And so the result of that last loop says that Joe must be in the admin group, and Joe has work mem set to 512. The other sidebar is changing of existing functions. So basically, once you create a function, it is an object in the database, and then other objects might end up depending on it, such as a view that calls the function or something along those lines, right? Now, in order to change the function, you always had to drop it, then you'd have to cascade that, and that potentially could get very inconvenient and ugly. So the functionality is provided to do create or replace. Create or replace just does a change in place without changing. Essentially, it doesn't change the object identifier of that function, so all of the dependent objects don't have to get touched. There are some limitations on when you can do this. You can't change the function name or the argument types. I'll get into that in a little bit later, but essentially the name of the function and the object and the argument types are what define to the system this specific object. That's how Postgres knows that I'm calling this function versus that function. You can't change the return type, and you can't change any of the out parameters, and out parameters essentially are the same as defining your return type. So those are essentially the same thing. So you would just say create or replace function instead of create function, and for quite a bit of what you would want to do in terms of changing a function, that just works. Okay, so now we're going to talk about the function argument syntax. So this is the whole bit of that first syntax for just the arguments. And specifically, we're talking about the argument mode. So the argument mode is an optional. You don't have to specify, but if you do, you specify that an argument is in, it's out, it's in out, or it's variadic. Basically, in is the default if it's not supplied. If you have out or in out, you cannot use that in conjunction with returns table, which is part of the returns clause that we'll talk about in a few minutes. If you use variadic, it can only be followed by out arguments. And the reason for that is it goes back to what I was alluding to a minute ago, which is the so-called function signature. The in arguments plus the function name kind of define what functions are going to get called. And with variadic, you're saying that I don't know how many arguments are actually going to get passed. So, but out arguments are really just placeholders for the return type, so they don't count as part of this signature that identifies the function. So variadic basically always has to be at the end, and you can have out functions after it because they kind of don't count for that signature purpose. And although it's not absolutely required, it's kind of good style. It makes your functions easier to understand if you generally define your arguments in order of in, out, and then out. So here's an example of one where I'm creating an in argument here, an in-out argument, and an out argument. Returns this amorphous type record. This is one of those pseudo types I was talking about before. It doesn't really, in and of itself, stand for anything, but these two out arguments have defined the return type to be basically a pair of ints. And you may or may not have ever seen this syntax. You can actually use the values clause just as if it were a select. So you can say values and in paren a set of values, and that's just like saying select those two values. So when I call this function, you notice I took the second argument and I'm outputting that first, and then I'm multiplying the two arguments, and so when I call this as 14.3, I get 3 and 42. Any questions about that? So the next part of the argument syntax is the argument name. So as I say here, most but not all languages can use an argument name in the function body. It's been supported now in Postgres for, I don't even know if I'd hazard a guess when it came in. It was probably an 8.2 or 8.3 or something, but I'm kind of showing my age here. When I first wrote PLR and when I first got involved with the project, Postgres didn't support arguments. These days, I think just about all of the languages that you're likely to run into will support arguments in the, named arguments basically for functions. And if you have an out argument, that's going to assign the name for the column that comes out. So in this example here, I've got the same function, basically, except now I'm naming the arguments. So I've got an in argument called A, and an out argument called mult, and an out argument also called A. And I do the same thing that I did before, but now when I call the function, because I've named the arguments, I can actually assign these arguments in either order because now they're named. So it kind of disambiguates your code if you use this. And I get the exact same result. The next portion is the arg type. This is required. This is, I think, pretty much the only thing that's absolutely required for the arguments. This is the type of the argument you're going to pass in. It can actually be schema qualified. So in other words, if you've installed, say, PostGIS into its own schema, and you're defining a geometry type, which is coming from PostGIS, you might have to schema qualify it here. Depends on how you set up your search path, actually. These can be base types. They can be arrays, composites, domains. They can reference columns using this kind of syntax. So you can say table name dot column name %type. And they can be these pseudo types. Any element, any array, any non-array. Is anyone not familiar with these polymorphic types in Postgres? A few people? So the basic idea here is that when you're creating a function, if you use one or more of these polymorphic types in the argument list and potentially in the return type, they have to be self-consistent. So in other words, if you use, let's say, any element in any array as arguments and you return any array, then at execution time, you could pass that function a text scalar or text array and it would return a text array. Or you could pass it an integer scalar, an integer array, and it would return an integer array. So obviously, if you want to use those data types, you better write your function in such a way that it's prepared to handle different data types. And that's especially important if you're writing your functions in C, because if it's not prepared, then you're probably going to end up with seg faults, which are potential security holes, right? So yeah, you have to be careful if you're going to use that, but it can be really useful if you want to do sort of the same thing with a lot of different data types, and you don't want to have to define a whole bunch of functions that are all basically exactly the same. You could just define it once, use those data types. So in this case, I've done that with any element, more or less exactly like the other example. But the difference is, I don't show it on the slide, but because I used any element here, I'm passing in floating point values, but I could just as easily pass in integers, and it would just work.
So record is a role that considers the polymorphic type.
Can you say that again?
Record returns record. It's also
Record is technically a pseudotype, not really a polymorphic type. In this case, because I've defined these as in-out, they kind of essentially are defining the output as being the same elements as, the same data types as the in. And in conjunction with record, I can do that. If I tried to use something more specific here, then it would have to agree exactly with these. But if you're going to use out on your arguments, you pretty much shouldn't bother trying to specify the output type in the returns clause. And we'll see more examples of returns when we get to that. So then you can also define a default expression. And so if the if the argument is not provided, that's what will get used. It's any kind of an expression that can be coerced into the argument type you can use here. And anything that's an input, so in, out, and variedict can have a default. Obviously, it doesn't make sense to have a default for the output. But once you've used a default for one of the arguments, all of the following arguments must also have defaults. And again, this gets into this, that goes back to the being able to resolve from the arguments that were passed what function we're actually calling. So as soon as we hit one that's got a default, assuming the user at runtime calls this function, doesn't supply that argument, then they're not going to supply any of the following arguments either, and they'll all get defaulted. So in this case, I've defined, A as an in, mult as an in out with a default of 2, and then A out. And so when I call this function now with just one argument, the default of 2 gets used, and so that's my result. So I've kind of hit on this a few times now, but here, I guess I did have a slide on it. This is function overloading. The signature that I was talking about is needed because Postgres does let you define multiple functions that have different sets of arguments. So the way Postgres disambiguates is using that signature. Something important to consider here is you want to avoid putting your own ambiguities in when you're doing this. So if you're going to create overloaded functions, you wouldn't want to create one function that takes an argument of real and one that takes an argument of double precision. Because now when you call it at runtime with 3.14, is Postgres using double precision or is it using real, which is less precision? You can probably guess that it'll use real, but you don't know for sure. It's better just not to get into that kind of situation. There's kind of an old restriction in Postgres also that the function name cannot be the same as an in-argument composite field name. And it's a very old historical artifact, and you probably will never run into it, but potentially could. It does come up every once in a while. And you wouldn't want to use a variedict argument that's got the same. You wouldn't want to have one function that was defined to accept like an int variedict and another one with the same function name that accepted just an int. Because the same thing is, do I call the variedict function with only one value, or do I call the one that's only got one argument? So here's an example where I create the same function foo. The first one is defined to take an argument of type text. The second one is defined to take an argument of type int. And in the first case, I'm just going to concatenate the argument to the word hello. And in the second case, I'm going to do a division and cast it to text and then concatenate it to was here. So I can call this exact same function name the first time with text and the second time with an integer value. And the right function gets called depending on the type of the argument. Any questions about that? Okay, so now we're on the return type. This is the syntax for return types. It returns a return type, or you can say returns table and kind of give it a column definition. Maybe you see this column name, column type, comma, column name, column type. That's a column definition list. So the return type is something that it says the return type value here is required if you're going to have a returns clause. As I said before, if you've got out elements, you could actually skip the returns clause entirely. It can return base, array, composite, or domain. It can also return a type based on a column in a table. It can use those same polymorphic pseudotypes. But then there's some additional pseudotypes for the return type that you might run into. Specifically, if you create triggers, trigger is a specific type of return. And if you want a function to be usable as a trigger, you have to return trigger. You can return void if the function is actually not going to output anything. If you're creating a foreign data wrapper, you use this foreign data wrapper handler. If you wanted to create your own procedural language handler, you would return this language handler. And you've seen us use record a bunch of times. So if you do skip the returns clause entirely, there's no way to make it return a set. It's only going to return one row. If you want to return a set, you have to basically have a returns clause, and you use this set of modifier, and we'll see examples of that. And if there is a returns present and there are out arguments, they need to agree. So here's an example of a function with an out and no returns clause. So I have two out arguments, no returns clause at all, you can see here. And when I call that function, it's going to assign these names and just... Now, because there is no returns clause, even though in this values clause, you see I actually have two rows. This is the syntax you would use if you wanted to have values output two rows. But I'm only getting one row out of this thing. And that's because there's no return clause and no way to specify set of. Whereas if I say this returns set of record with my out arguments like I had before in the exact same function body, now you'll see I get both rows. Another thing you can do is you can define a custom type. So this is sort of like when you return table and you're defining a column type on the fly for the function specifically. Well, this allows you to create a type that is stored in the system as a name type. So I can say create type and give it basically a column definition list. And then I can say I'm returning set of that type. And that'll do the same thing. Same result. And then finally, I can say returns table. So I can define my column definition list here without having to name the type. So now this applies just for this one function. To an extent, the reason you have so many options is because these things sort of evolved over time. You know, back in the 7.2 days, there was no way to return set returning functions. When it was first created, there was sort of a subset of these options were available, and over time, people had ideas of how to make it more convenient. And so now we've got basically 3 or 4 different ways to do the same thing. And here's yet another way, which again goes all the way back to the beginning of set returning functions, is I can define this function to return set of record without any out parameters at all. So you notice when I create this function at creation time, there is absolutely no notion of what that function is going to output in the definition of the function. The consequence is if you do that, when you call the function at runtime, you have to specify what the columns are going to look like. Postgres has to have a way to know what columns are coming out. So either you do it when you define the function or you do it at runtime, but one way or another you have to do it. This can be really useful if you've got a function that might return an unspecified number of columns. And kind of the classic example of this is the crosstab function in contrib table func. I don't know how many people have ever played with crosstab. And so that was, I wrote that when I did the set returning functions patch for Postgres. It was meant to be kind of the example of how to write a C function that does this stuff. And people complain all the time with crosstab that, hey, I don't want to have to define at runtime what my columns are, but unfortunately, Postgres needs to know that. Right, Andres? Yeah.
Could you define in your function and then override it at runtime if you wanted a different type to change it into text?
No, you wouldn't be able to do that. So basically what I usually end up telling people is if they need to do something like this, like specifically with crosstab, you typically end up needing to run 2 queries. The first one sort of figures out what your columns are going to look like and writes the second statement, including those columns, and then executes it. That is, I mean, people have looked at various ways to fix this over the years, but I'm not sure we've ever gotten a consensus on if there even is a way to really fix it. And Andres is shaking his head. Yes, I mean, that's essentially why Postgres requires you to know what the function, what the output is going to look like, because this is just a normal query. I could have another table in here and a join clause and join on that, the output of that function. And so Postgres has to know what those columns are. It's not really the same thing as something like SQL Server where they have real stored procedures. And a stored procedure in a language like, in a database like SQL Server, you don't call a stored procedure in an actual select statement. You say call or execute some function name, some procedure name, and it may have some kind of output, but it's not really the same as participating in an actual query. But because we are doing this in an actual query, that's a limitation. And again, people have talked about adding true procedures to Postgres, and there's been a debate over many years about it, but nothing has happened yet. So here's a function that returns type scalar, and just say, notice I can still say set of, so I can return a scalar int, but I can still do more than one of them. And here's a way that I could actually alias it. So one of the things you might notice if we go back here is when I called this function, this column ended up with the same name as the name of the function. If you don't like that, this is the syntax you can use at runtime to basically say, I want that column to be called F1 instead of the name of the function. This is something I use all the time. There's a built-in function in Postgres called generate series. How many people heard of that? It's really useful for testing stuff. Basically just generates a list of numbers. And there's different variants now that can do timestamps and other things. But basically, you can, if you wanted to run something 1,000,000 times, you can say iterate from 1 to 1,000,000. I'm a lazy typist, so I will usually say as g paren I, and then I can refer to the value from generate series as g.I, which is just 3 characters instead of generate underscore series. Now, here's what it looks like if I call a function that returns basically set in the target list. What I get is the full row type rendered as a row type. This behavior it's been basically deprecated for 15 years now. And I think Andres is working on fixing it in 10. Yeah. So yeah, anyway, you can do this in the target list. There are some odd behaviors, like let's say you have 2 functions in the target list that each return a set, but they return different numbers of rows. What should you expect? Postgres will do something, but it may not be what you expect. And here's a way that you can expand that back into individual columns, but now this thing is going to get evaluated multiple times per row. Okay, so now I'm going to talk about the attributes of functions, and I'm running out of time, so I'm going to have to try and pick up the pace a little bit. The language is obviously the name of the language that you want to write the function in. So we talked about it earlier. You can write functions in SQL, PL, PGSQL. There's some built-in procedural languages. There's external procedural languages. There's C and there's internal. We talked a little bit earlier about trusted versus untrusted variants. You can mark a function as being specifically for use as a window function. How many people are familiar with window functions? Okay, that's good. So Postgres comes with a set of built-in window functions. Generally speaking, we say that window functions can only be written in C. You can actually write window functions to some extent in PLR, and I've been told you can write them in PLv8. I'm not familiar with any other procedural languages that support writing functions in window functions. This is just a list of the ones that were built into Postgres as of, I think, 9.5. So volatility. Who here is not familiar with volatility of functions? Everyone here knows what volatility means? Wow. That's good. So we'll just touch on it quickly. If you mark the function as volatile, which is the default, it can change basically on every row. If you mark it as stable, it's not going to change within a given query. And if you mark it as immutable, for a given set of inputs, it should always and forever return the same result. You have to be a little bit careful about things like configuration settings. If you mark a function immutable, but it's returning a timestamp in a particular format that's determined by your system settings, that can mess things up. You build an index on that. You can have a variety of problems if you mark things as immutable when they really aren't. So these three functions, lower, now, and time of day, if you check the system catalog, you'll see that lower is immutable, now is stable, and time of day is volatile. And so if you called all three of those basically twice, you would see that, the lower function is going to give you the same value every time. The now function is going to give me the same value within one call, but it's going to be different from one call to the next. And time of day is going to give me a different value every single time it gets called. Behavior with null input values, you can say it's called on null input, which is the default, or you can say it returns null on null input. The important thing here is if you say it returns null on null input, the function itself doesn't even get executed. So if you know that's what you want to do, it's more efficient. The other important point here is let's say you're writing your functions in C particularly, if you allow null input and your C function isn't prepared to deal with that, again, you probably get seg faults. So it's really important to think about this one when you're creating your functions and make sure that your function is prepared to handle whichever choice you've made. So in this case, I have one that returns null on null input. The second one is going to be called on null input, and you notice I've got coalesce statements here. And so when I call those two functions, the first one is going to return, our null value basically, and the second one is going to return 9 because the null just got coalesced with 0. Leakproof. People familiar with leakproof? No? So Planner's allowed to push a function that's been marked as leakproof down into what's called a security barrier view. I'm going to go through this fairly quickly. Feel free to catch me afterwards if it's too quick, but I'll show an example of why that's important. This attribute can only be set by the super user. The function, this is again like immutable. Postgres is trusting you to do the right thing. So you could lie about this. The function should have no side effects and it should not reveal any information about the arguments other than the return value. So if I have this table, all books, I'm going to fill it up with some data. Basically, Joe and Tom are going to have books. And then I'm going to create this view that says, select from that table where the loser column is whoever's currently logged in. So the idea is Joe logs in, he can only see Joe's books. Tom logs in, he can only see Tom's books. I create this function, but I don't mark it leakproof. And it's going to say that if the argument is not the current user, it's going to raise a notice, right? And you notice that I marked it with a very low cost. So now when I log in as Joe and I call this statement with my leaky function, I get these notices that show me all of Tom's books. So this is a security problem. And the reason for that is because this function got pushed down into the view, essentially. So now if I drop that view and recreate it as a security barrier view and re-execute that query, now no longer do I see those notices. So no information is getting leaked. And that's because now the view gets handled first, and then this leaky function gets applied afterwards. But if I go in there and mark that function leakproof, I'm right back to where I started. So the lesson here is, make sure the function really is leakproof if you're going to mark it leakproof. Why would you want to use it? Because for performance reasons. There are certain things, if you know it's leakproof, it can get pushed down into the view. There may be performance benefits from doing that. Okay, security invoker and security definer. Basically, if you define the function as a security definer, it's like a set UID. Basically, whoever created the function, when someone else executes it, that function gets executed as if it were executed by the person who created it. So if you create the function as security definer as the super user, and then you give permission to a normal user to execute that function, just for that function execution, they get access to everything as if they were a super user. The default is just security invoker, which means the function gets called as the person who called it. So here's an example of creating a security, I create a table, insert a value into it, revoke everything from that table from public, create this function with security definer, and I'm doing all this as Postgres, create a user called guest, and now when I log in as guest, I can't directly select from the table, but I can select from that function because it was a security definer function. So this can be useful if you want to do selective access to something that you don't want to give general access. Everything has to go through your function. Optimizer hints, you saw on the security barrier example that I set the cost. These are parameters that are meant as hints to the optimizer for how many rows is this function going to return, how expensive is this function. I find in practice that it's really hard to set these things. I mean, you might set the cost down to something really low if you know that you've got a function that is pretty cheap to run and you want it to get pushed down into something. But generally speaking, this is kind of a trial and error type of thing. So here you can see I created the function with a specific cost in rows, and then if I look in pgproc, I can see that those are set. And finally, function local configs. You can set as we talked about earlier, you can set a specific configuration parameter, bind it to your function. So here I can say that this function is going to run with a work mem of 512. Another useful case for this is to set like a specific search path. And the function body. So the function body is typically this definition, which is just a string literal. It's parsed by whatever language you're using. It can be just simply a path to an object file if the C function name matches the name of the file. Dollar quoting is really useful here. And then if you're doing a C language function, you can typically will use this sort of syntax where you name the object file and the link symbol, which is just the C function name. So if you need to find, there's a special libdir, $libdir that you can use here, which is the path where the shared objects typically get installed. So you can say basically libdir / and then the name of your extension module, and then the name of the C function. If you want to find out where that libdir is on your system, there's a utility called pgconfig. You can say -- package libdir, and it'll give you where that is on your system. So these are just two different examples of function bodies. One as we've been seeing all throughout, and this is one that just defines a C function. And that's it. I don't know if I have any time for questions left or not. I think I have 1 minute. Any questions?
Can you talk about some use cases for using functions?
Talk about use cases? Boy, that's like boiling the ocean. I use functions all the time for many different things. I mean, you can create your own custom operators. You can create custom aggregates. You often will use functions for simpler things like where you're doing maybe the same calculation, the string for the calculation is like this long, and it just makes it hard to read your SQL statement, and so you can package it into a function body and then give it a descriptive name. And now when you call your SQL statement, it's just nice, compact, and makes sense instead of trying to figure out what it is that this long string is doing. Triggers are another very common use case. Yeah.
So all SQL statements in the else SQL functions are always prepared.
If the PL/PG SQL, if you've got a statement that's executing inside of it, it does get prepared and cached. If you're doing like a dynamic execute, I don't believe that's the case, no. Can't do that basically if it's dynamic. But when the function body gets compiled basically at runtime, the first time that gets cached. And so any plans that were generated as part of that are cached with it. And I'm definitely out of time now, so thank you very much.